right, so as I was saying in class today, we're going to be talking a lot about the tangent line, and we kind of went over the secant line representing the average rate of change, and the tangent line represents the instantaneous rate of change. All right, so let's talk about computing the instantaneous rate of change given just a couple of pieces of information. So we are told that the flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when the flash is set off. The data in the table describes the charge Q remaining in the capacitor at time t, and we want to use the data to estimate the instantaneous rate of change at the point where t is equal to 0.04, which represents the electric current flowing from the capacitor to the flash bulb. So basically, if I were to take these points and graph them, what that's going to look like, I'm just going to do a quick little sketch here with my time in seconds along the x-axis and my charge Q along the y-axis. Let's call this 100 up here, and we'll call this 0.02. So what the graph is going to end up looking like is probably something along the lines of that. And what we want to know is at the t value of 0.04, what is the instantaneous rate of change? So we basically want to know, well, if I were to draw a line through that point, what would its slope be? And the only piece of information that we're given is this. So the best that we could potentially do here is actually to take the 2 points around 0.04. So say that this was this point here and this point here. The only way that we're going to kind of get an idea of what the measurement of the slope would actually be to find the slope of the secant line through these points. So I'll say to estimate our slope at t is equal to 0.04. We're going to say the best we can do, and that's because of the given information, is to find the slope of the secant line I'm going to say that passes through.
Mr. Moriarty, please dial extension 1191.
The 2 points around t is equal to 0.04. So that's basically telling us that we want to use the points 0.02, 81.87, and 0.06, 54.88. And what we want to do is we want to use these 2 points and we want to find the slope. So we'll do 54.88 minus 81.87 all over 0.06 minus 0.02. So if I do that calculation, that's going to give me about negative 26.99 over 0.04, which is going to give me a slope of negative 674.75. And it says that that's representing the electric current flowing measured in microamperes. So sometimes we might not be able to find the actual slope of the tangent line at a specific point. Based on the data that we're given, we might need to go and actually find the slope of the secant line. That's going to probably be our best bet. So that's kind of the idea of the secant versus the tangent line. Like I was saying, this is kind of like 2 sections put together almost in one. So we're going to be kind of moving along to some limits stuff. So we'll talk about limits in terms of tables, and we'll review limits from graphs. So at the end of pre-calc, we had a little bit of an introduction to what a limit was. We're going to be talking about what a limit is in terms of a table. So we'll look to see what this is going to look like. So suppose the temperature from 6 a.m. to 6 p.m. on a given day is modeled by this function, t is equal to this whole rational function, where x is equal to 0 corresponds to 6 a.m. and x is equal to 12 corresponds to 6 p.m. So we want to know what the temperature is at 11 a.m. So at 11 o'clock in the morning, if we are following kind of the same pattern with x equals 0 is equal to 6 a.m., that was going to tell us that at 11 a.m., x would be equal to 5. So if I were to calculate what t of 5 is, I'm going to do 2 times 5 squared plus 30 times 5 minus 200 all over, and you can obviously tell that there's a problem already, all over 5 minus 5. So if I were to calculate this and do all that algebra, that's actually going to tell me that my numerator is 0, my denominator is 0. This actually ends up being an undefined value, which in the table below, you'll notice that I have these little dashes through 5. Well, that's because the function is undefined for 5. So basically what we want to know is, well, what is going on around 5? And not just around 5, but really, really, really close to 5. So you'll notice that I have 4.99 over here, and I have 5.01 over here. So let's take a look to see what's happening around. And I'm going to start with some bigger values, and then we'll kind of work our way a little bit closer to 5. So if I were to take an x value of 4, go ahead and substitute in for all of my x's and do my calculations, my t of x function is going to return a 48. So that would tell me that at the x value of 4, meaning at 10 a.m., the temperature would be about 48, if I'm kind of putting that into the context of the problem. If I were to calculate it at 4.5, we're going to 49. 4.9, we would get about 49.8. 4.99, we'd get about 49.98. And then I can do the same thing from the other side. So starting at x is equal to 6, which would be at noon, my temperature would be 52. At 5.5, my temperature would be 51. That would be 11:30. 5.1, we'd get about 50.2. 5.01, we'd get about 50.02. So you can kind of see what's happening as we're getting really close to 5. If I keep on making these values closer and closer to 5, like 4.999 or 4.9999 or 5.001 or 5.0001, our values are going to be approaching one value, which you can probably figure out is 50. So as our x values are going to be approaching 5, we can see that the t of x values approach 50. And we're just approaching 50 again, because as these numbers are going to get really, really close, these numbers are going to get increasingly close to 50, but never actually equal that. So what we can say is, we can say the temperature at 11 a.m. is about 50 degrees. So this is kind of like a real life limit problem. So we're saying, okay, as we're approaching this value, the y value, or in this case, the temperature is approaching a value. So that's kind of the introduction to an idea of a limit. So as f of x gets closer and closer to a number, which we were getting closer and closer to a number up here, L, and as x gets closer and closer to a number c from above and below, then L is the limit of f of x as x approaches c. So we use a limit notation, which I think you guys should be a little bit familiar with from pre-calc. The limit as x is approaching c of some function is equal to L. And this is an important thing. That's why I have it as an underlined and bold. A limit only exists if both the left-hand limit and the right-hand limit are the same. That's like key to what we're going to be doing with these limits with tables and graphs. So let's look at a graph. So I think in pre-calc, we talked a little bit about one-side limits. That means that we're looking from either the left or the right. So for this function f, what we're looking for is the limit as x is approaching 3. And you'll notice that there's like this little, can't say my finger the way, but this little minus sign here. That means that we're looking at the limit as x is approaching 3 from the left. Down here in part B, you'll notice that there's a little plus here. That means that we're looking at the limit as x approaches 3 from the right. So what that means in terms of the graph is that if we were to take a look at x approaching 3, so again, we're looking along the x-axis. So here's 3 on the x-axis. We basically want to know what y is doing. So if I'm looking as x approaches 3 from the left, I'm coming from the left direction. So I'm looking from this direction. So from the left, as x is approaching 3, my y value here is actually, and these are kind of misnumbered here. This should be -3 down below. This should be -2, which would make this horizontal line here a -1. So from the left, as we're approaching the x value of 3, the y value is staying constant at 1. How about from the right? Okay, so if we're approaching 3 from the right, that's this part of my graph here. So as we're approaching the x value of 3 from the right, my y value is staying constant at +3. And again, the limit is the idea as we're approaching the value. So it really doesn't matter that there's open circles here. We just want to know what's happening really, really close to or around that value. So if we know that a limit only exists from if both the left-hand limit and the right-hand limit are the same, well, the left-hand limit was -1. The right-hand limit was 3. So the limit as x approaches 3 of this whole f of x actually does not exist because the left-hand limit does not equal the right-hand limit. So we always want to kind of put that explanation in there as well. So if I'm saying that a limit doesn't exist, I want to know why. So that's because the left-hand limit of -1 does not equal the right-hand limit of 3. But we're also saying that f of 3 is a different value. That's okay. Like I said, we're only worried about what's happening really close to that value. We don't actually care where it's defined. So f of 3, we can say, is actually defined at +1. And that could be different. The limit could exist and the f of 3 value could still be different and it would still, the limit could still exist. So let's take a look at one more graphical example and then we'll kind of go into some special cases. So for the function g graphed in the figure, we want to find the limit as x is approaching 0 from the left of g of x. So here's my x value of 0 right here. And I want to know what's happening as it's approaching from the left. So from the left, my y value is 1. Then I want to know what's happening from the right, this little plus. So I'm looking as I'm getting up closer to x, the y value is also approaching 1. So since this left-hand limit is the same as the right-hand limit, we can say that the limit overall as x is approaching 0 of g of x is +1. So again, left-hand limit equal to right-hand limit, so the whole entire limit is the same. And then g of 0 actually in this case is 0. This is kind of what I was talking about in the last example. It doesn't necessarily need to be defined at 1. Your function could be defined elsewhere. Again, we're just worried about what's happening as we're getting really, really, really close. All right. So graphically, limits are pretty easy to kind of see. Sometimes in tables can definitely be misleading, and we'll see. Here's why. If we look at this table, if we want to evaluate the limit as x is approaching 0 of sine of pi over x, this is the table of values. If I were to take an x value of 1, plug it in here, an x value of -0.01, plug it in here, of 0.5 and plug it in here, you'll notice that all of these end up being 0. So we would guess that this limit as x is approaching 0 of sine of pi over x, we would guess that that's probably 0, right? Because we're looking and we're saying, okay, well, it's across the board the same. But if you were to actually use your calculator and plug this in, if you were in radian mode and you did sine of pi over x in your calculator, you would notice that it's going to look something like this. And as your calculator is graphing it, it's going to like literally continue to bounce in between these values. So that's what we call an oscillation. So what's happening is this graph of sine of pi over x is actually bouncing or oscillating between -1 and +1 forever. Like it's never actually going to ever stop. So even though our table up here is telling us that we really want to say the limit is 0, it's actually infinite because it's never actually going to stop bouncing in between those values. So we can say that in this case, when we have an oscillating graph, the limit's actually not going to exist because we're not just stopping at one single value. We're not approaching one single value. So again, sometimes a table of values can be misleading. Sometimes it can be a nice tool, but in some cases, the table might think or make us think that we're actually approaching a value that's getting really, really, really small, but it actually might approach a very small value, such as like 1 over like 10,000. So just be careful with the tables, and especially with these oscillations as well. All right, and one more thing that we're going to talk about before I'm going to have you guys try your homework is going to be infinite limits. So let's take a look at finding the limit as x is approaching 0 of 1 over x squared, if it exists. So if we were to make a table of values for these particular x values, again, I'm not going to show you the algebra, but it's basically taking these values and then just substituting them in and evaluating. 1 over negative 0.1 squared actually gets us a value of 100. And hopefully we can kind of see what's happening here as we fill in our values. If I plug in negative 0.05, that would give me 400. Negative 0.01 would be 10,000. Negative 0.001 would actually give me 1,000,000. I'm going to skip over this value for now because obviously if we were to put a 0 in the denominator, that would get us something that is undefined. I'm going to start from the other side. If I put in 8.1, that's going to give me 100. You'll notice that these values are going to be the same. 0.05 and squared in the denominator is 400, and then 10,000, and then we have 1,000,000. So what would happen if I were to make these x values even smaller? So like negative 0.000001 or 0.000001. You'll notice that these values are going to continually increase. They're going to continuously get larger and larger and larger as these numbers get smaller and smaller and smaller. So what we can say is these actually increase without bound. And then the same thing for the other side. These are actually going to continue to increase without bound. And as these numbers are getting really, really, really large in the y's and then the numbers in the x's keep on getting really, really, really small, we actually use the notation that obviously these are both approaching very, very large positive numbers. So we can say that the limit as x approaches 0 of 1 over x squared is actually positive infinity. But remember that in order for the limit to exist, both the left-hand limit and the right-hand limit have to be the same. And since they are both increasing positively without bound from the left and from the right, that's why we can make this conclusion as the limit is actually positive infinity. So if one was like negative infinity and one was positive infinity, then we would say that the limit isn't actually going to exist. So let's talk about why this is happening. So like, why do some functions increase without bound? Well, let's take a look at example 5, and we'll kind of see why this is happening. So example 5, we have a rational function. We want to find the limit as x is approaching 3 from the right of 2x over x minus 3. So if I were to kind of think about this in terms of what a rational function looks like, I've got two things going on. I definitely have a vertical asymptote down in my denominator of x is equal to 3. And if I look at my degrees in my numerator and denominator, I'm going to have a horizontal asymptote of 2 over 1. And then my branches are going to end up something like this. So my limit as x is approaching 3 from the right of this function, so here's my 3, my function is actually going to continue to increase positively. That's kind of what we saw in the table above. So what we would say as x is approaching this value of 3, we're actually approaching positive infinity because my graph is going to continue to grow positively. From the left, the limit as x is approaching 3 of this rational function, if I look from the left, my graph is actually going to be increasing negatively without bound. So we're going to say that the limit from the left is actually negative infinity. So why is this happening? Well, here's that vertical asymptote. So this is why graphs increase or decrease without bound, is because of these vertical asymptotes. So since there is a vertical asymptote at x is equal to 3, does the limit exist? Well, no, because one of the branches as we're approaching 3 is going upwards, and one of the branches as we're approaching 3 is going downwards. So like I was saying above, these have to be exactly the same in order for the limit to exist as a whole. So in this case, no, we're going to say the left-hand limit does not equal the right-hand limit. So what we can kind of conclude from this example is that when we do have some sort of limit that is infinite, whether it is positive infinity or negative infinity, we know that there's got to be some sort of asymptote at the value of a. So a is just some sort of constant or some asymptote on your curve. So that's all this part is saying down below, is if you have some sort of infinite limit, there's got to be some sort of asymptote that goes along with it. All right, so let me know if you guys have any questions on any of these homework problems, and I will see you in class next week.